All right here, folks. We got lots of slides here to get through today. Just to give you a heads up on the plans. Today, finishing 8-3. Next class, quiz. Class after that, test.
Let's go.
So I'm leaving.
You make it up when you get back.
Okay.
It's fine. When's the IA due? Today.
Like the first
No, wait, which
the
part?
other part.
No.
The day before the
Monday. The 8th, next Monday.
Monday the 8th is the whole hog paper. Okay? What's due today?
The
part 3 or
calculation.
4.
The Excel sheet.
How do you turn in your sentence?
Yeah, you know. There's a thing in the window that tells you how to name everything.
What's the history I do?
Huh?
The data, the final. The history, that's amazing.
Let's do that today, the final, right?
Yeah.
That's such a long
Okay.
Isn't it due Friday for you?
No, it's actually due tomorrow, he said. All of it is due tomorrow.
So, many of you, as in almost all of you, have yet to email me anything about the Excel sheet. So just kind of keep in touch on that. Some of us haven't sent an intro in. Keep in touch.
Oh, is that mine here? The extracts.
What?
Can I send my extracts to you?
The Excel file?
Yeah.
With your calculation done?
Yeah.
If you got a thumbs up back from me that said I got it, then you sent it and I got it. I tried to make sure I did that so that you knew that I received it.
I thought you said no here.
Oh, no, I said many of you.
Oh,
Many of us. Okay. But today, the main problem here is dealing with probability still. Let's get cooking because there's a lot of slides in this particular show. So, to recap, some of our basic rules for probability. A probability is a number between 0 and 1. If I look at the probability of the entire sample space, all the possible outcomes, that probability should sum to 1. In the case of equally likely outcomes, I just need to count the number of times that event occurs divided by the total number of occurrences to calculate a probability. And then the complement rule states that, this is so irritating to me. Fine. Just nothing. This won't work out either, probably. And the complement rule says that if I want to calculate probability of a complement, I can do 1 minus the probability of the actual event, right? So if we want to talk about expected value is really a really important thing. It's essentially the same calculation we did when we did the expected counts calculation for a chi-squared test. If you are a gambler, like expected value is what it's all about, right? If your expected return is less than the cost to play, you should not play that game. To calculate an expected value, you just take the probability of success and multiply it by the total number of trials. That'll tell you the expected outcome. So if the probability of rolling a 6 is 1 in 6 and we roll the dice 60 times, I'd expect 10 6s to come out. No 7s. keep in mind that expected values don't have to make sense in the real world. You can get 12 and a half heads, or 2.5 children, or this, that, or the other, but like doesn't have to make any kind of numeric sense. We've talked about mutually exclusive or disjoint events. We say that two events are mutually exclusive if their intersection is empty, or the cardinality of the intersection is 0. If you have mutually exclusive events and you want to find the probability of the union, you can just do the probability of the first event plus the probability of the second event, because there is no overlap between the two events.
The table on that provided is left required. But the slide.
This is all just recapping things we've done in 8.1 and 8.2 so far. Everybody's okay still? Okay, let's take a little pause here and do an example. So here we're given a two-way table. Suppose we choose a student at random and determine their gender and whether they have pierced ears. Find the probability that the student has A, pierced ears. What's that probability going to be? As a fraction. 103 over 178. The yes for pierced ears over the total number of students. B is male and has pierced ears. 19 over 178. Is male or has pierced ears.
The actual physical multiply. So what word like looking for in a current event that would indicate that it's talking about the money supply? Yes, that's it.
So it should be 90 males plus 84, 174 out of 178. So you have all the males plus the females with pierced ears. Everybody's okay with that? Or you could have taken all the males plus all the pierced ears and then subtracted off the males with pierced ears, because you would count that twice.
Don't worry about it, but you want to keep track of.
So again, just visually converting that two-way table into a Venn diagram. We did this last time as well, right? We practiced this. Okay. The general addition rule for two events. So if my events are not mutually exclusive, I have to be a little bit careful about how I'm calculating them. So if I look at this Venn diagram, notice that the event A and B is a subset of event A and of event B. So if I want to count up in the number of things in event A or event B, I can do that by counting everything in A plus everything in B, and then subtracting off the things in A and B, because I would have counted that region twice, and I really only want to count it once. Is everybody okay with this? Again, we've hinted at this in the last section as well, so if this sounds familiar, that's good. That means you're paying attention. Now the trick here is, notice we have two different formulas for A union B, the probability of A union B, correct? Yes? One is for A and B are mutually exclusive. One is for, I don't know if they're mutually exclusive or not. How do you tell if they're mutually exclusive? Their intersection is empty. So again, here is the summary of the two at the same time. One for mutually exclusive event and one in general. Note that mutually exclusive means the same thing as disjoint, or that their intersection is empty. That's what the probability of A intersect B equal to 0 means, right? That there are no things in the intersection. change up here. We're going to talk about independence now. So if two events, A and B, are independent, if the occurrence of one event does not change the probability that the other event will happen. Give me an example of an independent event. Flipping a coin, right? I flip a coin, I get heads. I take that same coin, I flip it again. Does the fact I got heads the first time change what's going to happen the second time? No. Right? Now, if I'm drawing names out of a hat without putting them back, does that change the probability? Yes. You okay?
Yeah, I'm just joking.
Okay, don't choke. Why does it change the probability? Less names in the hat for the next poll, right? There's a classic example of independent-dependent event. If our events are independent, I can calculate and events A and B by just multiplying the probability of A times the probability of B. Lovely, right? So the most common way of talking about independent and dependent events is talking about things happening with replacement or without replacement. So if I say the probability without replacement means that if we're drawing names from a hat without putting them back, without replacing them, that's going to change the probability of the next name draw because there's less names in the hat. If I'm putting the name back each time, I read it, Billy, put it back in, draw again, Susie, throw it back in, pull again, Billy again, like that's with replacement. If I'm putting the name back, does the probability change? No. So what can we say about those events? Independent, okay? So without replacement is code for dependent, with replacement, code for independent. Everybody's okay with that? So, for example, say we have 5 green gummy bears, 4 red gummy bears. You pick out one green gummy bear. What is the probability that the second gummy bear will also be green if I'm doing this without replacement? Drawing that first green gummy bear would have been 5 out of 9, right? Drawing that second green gummy bear without replacement would be 4 out of 8. Now there's 4 green gummy bears and 8 total because I'm missing 1 green gummy bear. How about with replacement? 5 out of 9 again, right? Nothing changed. Everybody's good? Okay. Just to make clear, mutually exclusive and independent are not necessarily related, right? So, for instance, flipping a coin twice is both mutually exclusive. You can get heads or tails, but never both. And independent, because the first flip doesn't affect the second flip. If you have a deck of cards and you draw 2 cards and look at their suits, that is independent. Is mutually exclusive because you can't get a suit that's both like clubs and hearts. But it's dependent because pulling the first card from the deck changes the probability of drawing the second card from the deck. So there we still have mutual exclusivity, but we lose independence. How about in our deck of cards, we pick one card and put it back. So if we look at the type of card, you can find loss of mutual exclusivity, right? You could get a jack 4 different ways, or get a diamond 13 different ways, right? Depending on what you're looking at there. And since you're putting the card back, you maintain independence. So there's an example of you lose the mutual exclusivity, but you retain the independence, right? So the goal of this exercise here is to show that you can have, or that the mutual exclusivity and independence are not the same thing. You can have one with the other, one without the other, neither of them. Anything can happen. All right, let's take a look at an example. Blood types of people can be one of 4 things. O, A, B, or AB. The distributions of random blood types for randomly chosen people in the US, China, and Russia are given below. What's the probability of AB for USA? How would I find that? You don't have to tell me the number, you should tell me how to find it. Add them up and then what? Subtract from 1. Good. There you're using the sample space as a probability equal to 1, right? If I add up all the possible outcomes, they better give me 1. Everybody agree? So 1 minus 0.43 minus 0.41 minus 0.12. So what is that? That's 84, 96, so 0.04. And for Russia, B, we do it the exact same way, right? 1 minus 0.39 minus 0.34 minus 0.09. Is everybody okay there? Did you know that blood type is tends to correlate a little bit ethnically? That peoples from certain regions are more common, have one blood type more commonly than others. Why is that? Come on guys, it's genetic, right? Blood type is genetic, right? If you're an A and your mother's an A, you can only have certain blood types come out of that, right? Can't get anything. Depends on what your parents are. Dirk lives in the USA and has type B blood. Type B can only receive types O and B in a transfusion, is what we're talking about. What is the probability that a randomly chosen USA citizen can donate blood to Dirk? Good. How'd you get that? So you did the probability of O or B. Are those mutually exclusive? Yes, you can't have blood type of both O and B at the same time. It'd be bonkers. So you can just add up the 2 probabilities, correct? Because they're mutually exclusive. Everybody's good? Okay. And you get the 0.55 as you guys said right away. What's the probability of a randomly chosen person from the USA with type O blood and a person from China with type O blood? So you're choosing 2 people. What's the big question you have to ask yourself before we talk about how to do this? Are they independent? Are those 2 events independent? Choosing a person with O blood from the USA and then choosing a person with O blood from China. Yes, right, because removing the person from O blood from the USA doesn't change the probability of drawing the person with O blood from China, because they are in different populations. Everybody agree? Okay. Unless somehow this person from the USA is able to get on a plane and get to China, somehow between choosing him and then choosing the person in China. Yeah, I mean, if he can like fold space or something, sure. All right, so they are independent, so how do we calculate it? Probability that the person has O blood in the US times the probability the person has O blood in China. Okay? You know, just like the probability of flipping a coin and getting heads one time in a row is a half. Flipping a coin and getting heads 2 times in a row would be 1/2 times 1/2, or 1/4. 3 times in a row, 1/2 times 1/2 times 1/2, 1/8, etc. Lucas.
I don't want to sidetrack, but I have a question. So for the quiz, is it going to be 8-point test? No, we quiz then test. That's what I was asking. Is it just going to be 8.1 and 8.2?
Let me get through this and I'll look up and double
Okay.
check that for you. Totally feasible question. I just don't want to do it right this
No, that's
time.
fine. That's not derail his.
Yeah. No, it's okay.
That's why I started with I don't want to sidetrack.
Yeah. I'm just going to ask you to table that till I'm
Yeah, that's
done, and then
fine.
I'm happy to look that up, but you're going to have to remind me because I'm probably going to forget.
That's fine.
Okay. Probability of choosing 3 people, 1 from the US, 1 from China, and 1 from Russia, all with type O blood. Is this independent?
Yes.
Yes, because they're all coming from different countries. So, how do I do it? Multiply 0.43 times 0.36 times 0.39. Just over 6% chance of doing that. Everybody cool? Cool beans. What's the probability of randomly choosing 3 people, 1 from each country, all with the same blood type? So, how many outcomes are there to this?
4. There's 4 different.
Oh, there's what? Are you serious?
4. You could pick 3 O's, 3 A's, 3 B's, or 3 AB's. Everybody agree with that?
Yeah.
Okay. What's the probability of choosing all 3 O's?
6%.
We just did it, right? 0.43 times 0.36 times 0.39. Or, which means what symbol in probability speak?
Yes.
Plus the probability of getting in 3 A's. How would we calculate that? 0.41 times 0.27 times 0.34, or, which means plus 3 B's, which would be 0.12 times 0.26 times 0.18, or, which means plus 3 AB's, 0.04 times 0.31, or 13 times 0.09. So shade over 10%. Is everybody okay there? Why was I able just to add up the 3 O's, 3 A's, 3 B's, and 3 AB's and not have to worry about subtracting anything? We took advantage of something going on here. Intuitively, we didn't say it, we probably should have, or checked it anyways. blood types are mutually exclusive. You can't be both A and B at the same time. Those are two different things. Even though there's one that says AB, it doesn't mean that you're both blood type A and blood type B. It's like some third thing that's a little bit of each. Biologists, I don't know, you talk about this in AP biology?
AP biology, I'm in AP biology.
Do you talk about blood types?
Oh, not yet, but we're gonna get to
We
it.
did last year.
You did an HL?
Yeah.
Yeah, so you know all about the blood types.
Well, what's I know?
I wouldn't say I know a lot about it.
Okay.
Learn it. Not.
Okay, so one could assume that you would know these things. Whether you still do or not is a different story. But at one point you were expected to have known all about them. Okay. New example. It's estimated that 17% of all computers bought from one manufacturer require one repair job during the first month. That 7% will need repairs twice in the first month. And that 4% will require 3 or more repairs in the first month. What is the probability that a computer will require no repairs?
83.
So let's start by building out some notation. So we have 3 separate events here. 1 repair, 2 repair, 3 repair. So I'm going to define those as events A, B, and C. And we have those respective probabilities. Everybody's okay? So I introduce some notation, write down my knowns. Consolidate that at the top of the page. So, no repairs. That event is mutually exclusive to the other ones, correct? You can't have no repairs and then also have 1 repair, or 2 repairs, or 3 repairs, right? So if I add up, it should all equal 1. I suppose in this maybe it's ambiguously worded, right? That 17% of all computers bought from one manufacturer require exactly 1 repair job, exactly 2 repair jobs, exactly 3 repair jobs. So we probably should have included the word exactly there to know that the 7% that need 2 repairs isn't part of the 17% that needed 1 repair. That there's some mutual exclusivity across the board here. Is everybody okay with that? Did a poor job of writing that question. What is the probability that a computer will require no more than 1 repair job? What does no more than 1 mean? Or 1 or 0, right?
Shoot.
So that could be no repairs or 1 repair. Those are mutually exclusive, correct? Because you can't have 0 and 1 repair at the same time. So we can just add up those 2 probabilities and there you go. Again, notice on all these problems we've done so far, the actual mathematics involved, the calculation, really easy. All we're talking about is multiplying and adding and subtracting and stuff. It's like super simple. What's the hard part? Setting it up, right, to get to the right answer. Okay. What is the probability the computer will require some repair? What does some repair mean? 1 or more, right? Not just more than 1, but at least 1. Easy peasy, right? Assuming you know what you're reading. Everybody's okay? Again, what did we take advantage of in order to just add them up simply like that? Mutually exclusive. Or what other word could you use instead of that? Mutually exclusive? Disjoint. Yes. Okay. Also worth noting here, you could have used the complement rule. At least one repair is the same as not 0 repairs. Right? So I could have done 1 minus no repairs. 1 minus 0.72 is also 0.28. Either way of doing it is fine. Depending on how many things you had going on there, the complement rule could have been much easier, or what you had to calculate. But in this case, there's not much difference, right? Adding up 3 things is not much more difficult than subtracting 2 things. All right, if you bought 2 computers from the manufacturer, what is the probability that neither will require repair? Good. So, what is the key part of reading this that you have to understand about the events that are happening? They are independent, right? Me buying 1 computer isn't going to affect whether the second computer needs repairs or not, right? So this is just going to be the probability that the first does not need repair times the second does not need repair. If you remember, we computed the probability that the computer needs 0 repairs as 0.72 earlier. So I'm just recycling that answer. So we get like 50-ish% there. Oops. Oh, come on. So 0.518, if you're writing this up. All right, if you bought 2 computers from the manufacturer, what's the probability that both will require repairs? Okay, so same idea as last time. So 0.28 times 0.28. Yup. I used the 0.72 because up at the top I written down no repairs was 0.72, and I added that to our list of probabilities. But if you had the 0.28 written down from earlier, you could have certainly just used that number as well. No big deal. Everybody's okay? Once again, we have independence going on here along with mutual exclusivity that we used to do that. All right. Next idea, conditional probability. Okay, conditional probability. This is calculating the probability that some event will occur given that some other event has already occurred. So the notation we use for that is P, and then the event that we're concerned about, and then we write a vertical line, and then the event that has already occurred. Okay, sorry here. Come on. This PowerPoint is too big. So the way you read that set of symbols there at the bottom is the probability of B given that A has already occurred. Or given that A has occurred, right? Everybody's okay? So if you're talking about drawing a card, you could say, what's the probability of drawing a heart, given that a heart has already been drawn?
What? A heart's already been drawn, so there's only 12
Why are you yelling?
Okay. So, for a conditional probability, we can use the formula as stated below. The probability of A given B is the probability of A and B divided by the probability of B. Notice that the probability of B given A is essentially the same thing. You just swapped where the A's and B's are, right? What is the same in those two formulas? No, there's one of those values is exactly the same. The numerator is exactly the same value because A intersect B is the same as B intersect A, right? It's just the overlap between A and B. So in each of these two formulas, the numerator is the same number. Everybody okay there? Correct. So just, that's me reminding you guys that regardless of what condition it's under, A or B, the numerator is the same. The denominator, though, is different, right? The denominator is always the given, right? Or the condition, let's say. So let's start by doing an example using a two-way table. So it says, consider this two-way table below. You have the event E, which is a grade comes from an EPS course. That's Engineering and Physical Sciences. And L, the grade is lower than a B. So find the probability of L. The first thing that I would do here is calculate some totals. So that's what I did there, is I just added my rows and columns. How many total students did we have? 10,000 here, right? What's the probability of L? $36.56 out of 10,000, right? What's the probability of E given L? So the formula is the probability of E and L. What is that? It's 800, right? There's 800 students in an EPS course that got below a B. Divided by the probability of L, which was the other one, right? What we just did. Notice since they're both out of 10,000, I dropped the 10,000. Technically, the numerator is 800 out of 10,000 over the denominator 356 or 3656 out of 10,000. I just dropped the 10,000s to make it less cumbersome as a fraction on top of a fraction. Is everybody okay there? What if we did the opposite, the probability of L given E? What's going to be the same? The numerator. Great. What's the denominator going to be this time? EPS, which should be 1,600 out of 10,000. Everybody see it? Got it? Got it? Got it? Good. That went too fast. Okay, so before we saw that if we had independent events, we can just multiply the probability of each event for an AND situation, correct? AND means multiply. However, if our events are not independent, that they are dependent, we need to use a conditional probability. So the probability of A and B is the probability of A times the probability of B, given that A has already occurred. When do you need to use this formula? When you have dependent events. Okay? Will this rule also work if you have independent events? Yes, because the probability of A, or probability of B given A, if A and B are independent, is just the probability of B. Everybody all right? Let's look at some examples here. All right. This is going to be one where drawing a tree diagram can be really helpful for us. So when we're dealing with these dependent events, this is almost always the go-to way of visualizing what to do. So consider flipping a coin twice. So I toss a coin. My first toss, it's 50-50 heads or tails. If I get a head, it's then 50-50 heads or tails. Or if I got a tail, it's 50-50 heads or tails. Everybody agree? Everybody's okay with how I constructed this? Or each split is the possibility of a coin toss. So I have my first toss, and then depending on what I get, I have a second toss that happens. Okay. Just looking at what we have here, if I go and I look, we have 4 separate outcomes because I have 4 branches to this tree. My first branch is heads, heads. My second branch would be heads, tails. My third branch would be tails, heads. And my fourth branch would be tails, tails. Everybody agree with that? And for example, the probability of getting 2 heads is going to be 1/2 times 1/2. So that's the probability of heads times the probability of getting heads, given that we've already gotten heads. Everybody's okay? Let's do one where, so why is this dumb?
What?
Why is this a dumb example?
Because everything's 1/2.
Why is everything 1/2 though?
Because there's 2 options that match, or 2 results.
What?
Mutual exclusive.
Oh, not that one.
Independent.
Independent! Coin flips are independent. So the conditional probability is the same as the unconditional probability. That's why it's 1/2 all the way through. Everybody's okay? Let's look at another example where we don't have that same independence. So it's a little bit more complicated. You guys ready?
Yes.
I need you to lift up one side of your cheek. Put a hand under there. Lift up the other side. Stick your other hand into there. And then hold on to your butts.
Why is no one doing it?
I don't know. Lucy's the only one following directions.
Yeah, come on, guys.
Lucy, don't stick your hands.
All right. It says the Pew Internet and American Life Project finds that 93% of teenagers use the internet, and 55% of online teens have posted a social networking site. Whatever. what percent of teens are online and have posted a profile to a social networking site? Whoa, this sounds pretty confusing. What should we do? I'm gonna draw a tree diagram.
A tree. Oh,
Yeah.
a tree for this one.
So what's my first split in the tree?
Teenagers.
Teenagers that use internet and who
Can
don't.
you stop?
Great.
Means everyone?
Online or not?
Anthony?
And then
Friends of
if they are online,
There's
my
another-
second split's gonna be
If they post or not.
have a profile or not.
Mm.
Good.
Yeah.
So here is my tree diagram. Online, yes, is 0.93. So not is 0.07 because it has to add up to 100. 55% of them have a profile if they're online. So 0.45 don't have a profile because what do these probabilities have to do? Add to 1. If you are not online, can you have a social media profile? No. So it's 0 for yes and 1 for no. Is everybody okay with how I constructed my tree diagram? So we're asked for percent of teens online and have posted a profile. So I need to track this path, right? So the probability of online times the probability that we have a profile given that we are online. Does everybody feel okay there? Again, what's up?
Does it mean profile, the probability of profile times online, or divide? Because I thought the last example was like divide.
This is the word that means given that. Doesn't mean it's division.
So you times the probabilities together to figure it out.
No.
Well,
So that's the conditional probability. It has its own separate formula. In this problem, it was given, the value was given to us in the question. So I didn't do any computation to figure out the probability that the teenager has a social media profile given that they're online. Because that probability was told to me in the problem. Does that feel okay? So you didn't actually compute that number at all. Are we okay? Nicole's making faces. Reading's hard, guys.
I think I just need to practice this more.
Good, because we're gonna do some in-class examples here.
Yeah, you should make someone.
But here's the thing, we're on slide 36, there's 62 slides.
What?
I
62?
think so.
No.
All right, here we go. We're more than halfway, 72 is, 36 times 2 is 70.
76. Flip it around.
All right, in an experiment, researchers place
So you did it.
6 green toys and 4 red toys into a container. The child is asked to select 2 toys at random. What is the probability that the child chooses 2 red toys?
It's so funny.
Build a tree diagram. Red or green is my first choice. Red or green would be the second choice. Everybody's okay with the tree that I built? Red or green. Those are the only 2 toys colors in there.
Okay.
So the outcomes are red and green and red, or green and green.
Okay, making places one of the.
I want the red and red track. So the probability of drawing that first red toy would have been 4 out of 10.
But then it goes to 3.
Drawing the second red toy would be
3, 9.
3 out of 9.
Yes.
Because we've removed a red toy from there. So the probability of drawing 2 red toys then would be 12 out of 90.
Yeah, out of 90.
12 out of 90.
Okay.
Yeah.
You could add that.
Did you give that, Katie?
Yeah, I understand now.
It's a probability of harm.
And all of these four answers, these are all acceptable answers, right? Fraction, reduced fraction, decimal, percentage, all of them acceptable.
Sit down.
I actually get the brain blood flow when I'm standing.
All right, another example. A survey for 1,000 people was performed regarding their gender and whether they were colorblind. The results are given below. What is the probability that a person chosen at random is colorblind, given that the person is a female?
2 out of
Does that mean you?
40,
two-
oh, 1,490.
2 out of what?
No.
1,000?
No, the answer is
2 out of
1,000.
That was just
2
I said
out of
2 out of
490.
2 out of 490.
good.
Giving
job.
that to female because they embarrassing. Yeah, that's bad. That's really bad. That was easy. I don't even know what I'm doing.
So again, the formula is A and B divided by the probability of B. So the probability that we are female and colorblind, 2 out of 1,000, divided by the probability that we're female, 490 out of 1,000, or you could just leave the thousands off because they're the same and write it as 2 out of 490. Everybody's good?
Yeah.
Okay. What is the probability that a person chosen at random is a colorblind female?
1,000.
No.
Yes, it is.
Yeah.
Yes, it is.
2 out of 1,000.
That's right.
No, that's right.
It's
It's
allowed.
allowed.
It's allowed. What are you laughing at? It's
1 over 500. No, I think this is 3 out of like 67.
What did you just say?
What is the probability that a person chosen at random is a colorblind individual?
42 out of 1,000.
Actually, 21 out of 500.
Oh my god.
You got jokes today. You got wrong answers.
Oh.
All right. These tend to be the hardest scenario ones.
Okay, we need a lot.
The probability that a regularly scheduled flight departs on time is 0.83. The probability that it arrives on time is 0.92. And the probability that it arrives and departs on time is 0.78. Find the probability that a flight arrives on time, given that it departed on time.
So you do some subtraction? Do you just subtract?
Wait, we need that formula. Don't we need that formula?
Yeah, that formula.
Oh,
You
where's the
haven't memorized it
formula?
yet?
Write it down.
The formula for the givens.
Yeah, it's the probability
It's
of both of
something-
them over the probability
Yeah.
of the given.
Yeah. Okay, so let's do it. Let's do it. We can do that.
You're right, we did this last year.
We need to put in the calculator, that's what I mean. We didn't do this exact problem last year.
No,
we didn't.
Oh.
Yeah.
Yes.
Good job.
Yes.
I have a feeling I might get this wrong on the quiz or test.
Oh.
These are, again, if you know what you're reading, there's nothing really to do here.
Okay.
The problem is
Memorize.
knowing what you're reading and being able to go, oh, there's conditional probability here. Oh, I need this formula.
I'm gonna mess
Oh,
up the
it's
formula.
independent dependent.
I know the
Oh.
formula, but I don't know the formula.
Make up the entire chapter.
All right,
Yeah.
departs on time given that it arrived on time.
Okay.
0.78 over 0.92.
5, yeah. Okay.
Okay. How is conditional probability related to independence? If A and B are independent, the probability of A given B is equal to the probability of A, and the probability of B given A is just equal to the probability of B. That the event, that the one preceding it happens, has no effect on the other. Or, if the probability of A and B is equal to the probability of A times the probability of B. So you could check either relation to show that two events are independent if you're given probabilities. So either relation is okay to show independence.
Wait a minute, is the first one just?
Okay?
Yeah.
I love it. It's the halo effect. It's like, Mr. Kulik, what's that? Never mind, I got it. Just saying my name somehow
Yeah, just really
loosens,
connected the dots.
loosens it up in your head, and like the correct answer comes tumbling out on you. All right. Let's practice doing this then.
Okay.
The probability that a regularly scheduled flight departs on time is 0.83. The probability it arrives on time is 0.92, and the probability that it arrives and departs on time is 0.78. Are these events arriving on time and departing on time independent? What would I do to check this? The formula, which would say, which formula should I check?
Would it be 0.7883?
What I would do is I would check, does P of A times P of D equal P of A and D? Because I have those three things given to me, right? I don't like this method. Don't do that. I don't like that method. Don't do that.
Do the one that you said.
Do this method. That's the one that's the easiest one to do, right? Because all we have to do is plug in our numbers and see if they match. Do they match?
No. Yeah.
No, they don't. What do we conclude? They are dependent.
Does not independent count?
Yes.
Okay.
Not independent would be the same as
Doing
dependent.
way too much.
But it's more letters.
We're not having a party tomorrow. It's the 12th. No, it's not. I mean, it says party. It says it's it was supposed to be the second. I'm
Okay.
sorry about it, but it was supposed to be tomorrow. It is tomorrow. The problem is
All right.
don't bring it.
Example, another one. In a certain country, police. Your Chinese field trip can make party. Oh, excuse me. In a certain country, the police stop drivers on suspicion of drunk driving. When stopped, drivers are either given a breath test, a blood test, both tests, or neither. Records show that 81% of drivers are given breath tests. 40 are given blood tests. 25 given both. What's the probability that a driver is given a test?
Make it true.
80 plus 40 plus 25.
No, it's not. It was bad.
Oh. Wait, it's gonna have one. Oh.
Never mind. Actually,
Let's draw a Venn diagram.
That's a good idea.
That's
Better.
yeah, actually.
Both? I understand.
So you subtract.
Oh, yeah. Subtract 25 from the blood and breath. 5.
Everybody's good with what we did there?
Yeah, that's done.
Okay, so what am I gonna do? What's the probability then?
0.96.
Or you could have added up 0.15 plus 0.25 plus 0.56, that's the same thing. Yes, that would be correct. 0.4 received null.
Wow.
Probability we're given exactly one test.
0.7.
Good, how'd you get it?
0.15 plus 0.56.
Good. And exactly one test is mutually exclusive. Because you can't have one test and get both blood and breath. That's crazy, Mr. Kulik.
Yeah.
That's more than blood and.
That's more than
Wait, how did
one.
it do it?
Unless they give you a
Poke your finger.
brood test or something.
What's that?
Well, breath and blood.
Oh. Okay.
I feel like
Brood.
if you're breathing blood, that's might be.
Oh, there you go.
Oh.
What if you're blood and breath though?
That's not.
That sounds like all the shoes.
That's like a dark strict TV.
All right.
That's Moab.
Probability, no test. We already stated this, right? 0.04.
No test.
Yeah, you saw it coming. All right. Are they independent?
Don't be nervous. Yes.
How would you know?
You haven't done the test yet. She's getting.
How would you check?
50-50 chance. I mean, you check because you can't read blood. No, it's not. I
Yes.
Yes? Multiply them. Oh. What are you doing? I don't know.
So again, since we had the intersection, I suggest checking if probability A and B is equal to probability A times probability B.
So it's independent. No? No, it's dependent. They don't equal. Oh, they don't.
Okay.
I see.
I could've gone other way.
It is a 50-50 guess. But I'm gonna tell you, if you don't show any work, you're not gonna get 50-50 points. All right.
I'll try.
Oh, who loves geometry?
We only
I
have
like
geometry. I'm so geometry.
I low-key forgot all of it.
All right. Shh. The radius of the board is 40 centimeters and divided into 3 regions. You score 2 points if you hit the center, 1 point for the middle white region, and 0 points for the outside region. What's the probability of scoring a 2 in one attempt?
Oh, wait, no, but it's the diagonal.
20.
Is it 5? Sorry. It's 10.
Which means that it would be
out of
35. It would be 5.
Okay. Reminder, what is the area of a circle? Formula. You guys are so sad.
Pi squared.
Oh my
He
god.
has a pi in it.
Nobody's even 7 yet.
I love pie.
Pi r squared. Thank you, Daniel.
I got the pi part.
So our plan for this should be the area of the 2-point region divided by the area of the entire dark. So pi times 10 squared divided by pi times 40 squared.
Oh, that's weird. Yeah, that makes so much. I don't know what you're talking about.
Now, we made a little bit of an assumption here. What's the assumption?
Making one attempt.
What?
I don't know.
Since you always hit the dartboard,
Oh,
right?
I know.
Who's thrown darts and missed the dartboard before?
Wow, that's L or
Only 3 of you guys.
Yeah.
What for great agency here?
It's how I got holes in our
The
wall.
line?
Good things happen.
Julia has darts. Yeah,
Let's say 10 feet.
Yes, I am. I know. Oh, yeah, darts. You a dart. I never hit her wall.
How about the probability of scoring a 1?
That's different, probably.
It's the same.
Is it the same formula
Yeah, it's
but
the same.
different?
10.
What shape is the white region?
A circle. It has
It's
a hole.
not a circle.
It has a hole in the middle.
Yes, it does.
It's a
have
donut.
It's a donut. So it's going to be the same formula.
But not the radius.
It's going to be the area of the white region divided by the area of the whole dartboard. To calculate the area of the white region, you do pi times 20 squared minus
Minus 2.
pi times 10 squared.
Oh.
Those are the ones in the back.
And then we just plug this in.
Yeah.
I just remember thinking that SAT and CS.
Yeah.
Why should I be like, uh-oh?
Yes.
You guys are so
6,
making me so
7.
sad.
That was my freshman year.
Why'd you take that SAT?
No, like I,
Wait, what did you
no, like I took like geometry in my freshman year.
Yeah, just don't forget
Oh,
stuff.
yeah, geometry is the easiest part on ACT. No, it was. Okay,
Okay.
actually, some of the
It
ones on ACT
depends.
are so.
All right. Next thing we want to do is talk about these at most and at least questions. The thing to keep in mind here is for at least and at most questions, the complement rule is often faster. Do you have to do the complement rule?
No.
No.
No. But you're recommended.
But it's often going to be a little bit quicker. And since you don't have unlimited time to take your test, should get in the habit of trying to do things the fastest way possible, right? All right, let's read the example. Suppose that the probability of there being rain on a given day is independent of there being rain on the day before or after. Over the next 4 days, you determine the probability that it will rain on any one of the given days is 30%. What is the probability of it raining on day 1 and day 2? So notice that it just is asking about day 1 and day 2, not about day 3 and 4, so we don't care what happens on those days. So the probability of rain on day 1 times the probability of rain on day 2. And we can do it this way because we're given in the problem that rain is
Independent.
So 9% chance of rain both days.
I put things in my calculator wrong and I had the idea right and I can get the wrong answer.
So if you have the right numbers written down on your paper, that counts for a lot.
That's
Okay.
Okay. What is the probability of it raining on day 1 or day 2? Nope.
Oh, it's different. It has a little.
Wait, Crystal,
That's the line, right?
Yeah.
Yeah.
But it's only one now. But it only. No, I don't.
How is it back?
Oh, it's blood. No, mine is up. I see.
Both?
Oh, I see.
Wait, wouldn't that just be mine? Wouldn't that be?
I understand though. Cause they're at
Oh, I see.
it's at 1%.
Gotcha.
Okay. It's the probability of it not raining on any one of the 4 days.
Oh, 70 times 70?
Times 70.
Here's what I would do. Well, it could be not raining on any one day. Oh, sure. Yeah, that's fine.
There's still 4
Oh, I see what it was asking.
Oh,
So just not one of the 4, just a one day.
Oh, I thought it meant
On any
every
one day, I see.
Yeah, I
I misread
One
it
day,
too.
yeah.
It's a daisy, guys.
Maybe it's a
Wait,
day for
but
everyone.
if it was the other way, would we just do 70 times 7 times
Yeah.
7 times 7?
Yeah.
Okay, good. That means I got it.
What is the probability of it raining at least once?
No, raining, no.
Wait.
No.
30?
So that means it could rain one day, or 2 days, or 3 days, or 4 days, right?
If you're gonna answer the question, don't just say no to other.
You.
How many different ways could it rain one day?
If you know the answer, then say
One.
4. It could rain on day 1, or it could rain on day 2, or it could rain on day 3, or day 4. How many different ways could it rain 2 days? 4.
Oh, at
1 and
least
2, 2 and 3, 3 and 4, 1 and 4. How many different ways could it rain 3 days? 3. Did not rain on day 1.
Oh,
You
yeah.
know, like.
Yeah.
All right. So you get the idea. This is going to be enormously obnoxious to calculate, right?
Yeah.
Or what else could you do?
Calm.
Compliment. Yeah. What is the same thing if raining at least once?
Not raining.
Not 1 minus not raining.
Wow,
One
that's
minus not
very
raining.
Let's do that.
redundant.
Blah 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 blah. blah.
One minus never raining. Oh wait, what was it?
That was what you calculated last time.
I
You
know,
see?
I forgot it though. It was like 9
70.
Oh, it's your point. Okay.
We were doing it.
Oh wait, I said that, but we didn't actually calculate.
Yes.
Okay, so then it's 1 minus that.
Yes. Get it.
Yes, you see, you just.
Good lord, guys.
Yeah.
Moab?
I feel like the people listening to this at home are gonna really enjoy today.
Oh, there's
a weird day.
like if you brought in the hottest chocolate bar to exist, would you try a slice?
No. I do not like spicy.
It's the hottest chocolate bar to ever
Mother of
exist.
all bars.
All right.
Mother of all bars.
What is the probability of it raining at most 3 times? What does that most mean?
No more. 3.
Three's max.
Three's
Three's
max.
max.
Okay. How would I do that? That means it rains 0 days, or 1 day, or 2 day, or 3
The
days.
probability of 4 of it raining all 4 days. Then you do 1 minus that.
Yeah, let's do that.
No, I didn't even touch you.
Complement rule.
I would you want to?
No.
It's not. It's not.
No, because the probability of rain and not rain is not 50-50.
That's
Oh, okay.
not.
All better.
So there we go.
Thank you.
Yeah, I know.
That's a lot.
Well, if you think about it, it's pretty rare for it to rain all 4 days if it's only 30% chance of rain each day. Anthony, what's up? Short, but not in your chair.
What?
Shoot.
I know.
You got through 62 slides.
Yes, we just
Oh,
did
we
it.
did. Wow.
We're so productive. Oh, sorry.
There's nothing.
Wait, is the quiz is next class.
Now there's a quiz.
Yeah.
Oh yeah, we have to look
What?
up that
Yeah,
thing.
Oh, yeah.
Oh,
That's okay. It's,
The quiz is.
I still have I need cheese.
well, let's do that. But I got that. I'm pretty organized. Yeah, there we go.
Alright, folks, I'd like
Oh,
to
Venn
check
diagram.
in.
It's all Venn diagram.
Draw and label a Venn diagram from a description. Fill out a two-way table from description. Answer question using a Venn diagram or two-way table. Fill out a Venn diagram with 3 sets. Identify sets in a Venn diagram. That is, combinations of unions, intersections, complements, etc. Use a Venn diagram to identify the number of elements contained in a set. Combinations of union, intersection, complement, etc. What is this covering? 8.1 and 8.2.
Perfect.
Nothing that we did today. Okay? Quiz next class. Test the class after. I know.
This lesson was
So then is there like a review that's going to be on that?
No. Because I don't want to have to check them.
Okay, but is there going to be 8.3 that's due on Sunday?
Yes.
Yeah, that's right.
You should do the 8.3 homework. There's 25 questions.
Oh, wait, there's something.
Yeah.
I agree. Those questions are like, it's like, there's 8 questions and then every question's like,
I remember what's
No, not
one
every
through
single
10?
one is like
No,
that.
like if you realize like if you count the 8, like all of it was like 70 something. No,
There's
No,
actually
you don't do it.
there's
No,
actually 21.
no.
There's actually 21 for 18.
Oh my God.
I actually want to